Okay, so here we are in March, and here's our calendar. I want everybody to check it out and make sure you give yourself some time to do this pre-lecture because it would be really helpful. All right, so let's go straight to the document camera, and let's begin today's lecture. All right, so what we're going to be doing today is inference for simple linear regression. So what's simple linear regression? That means we just have one x variable predicting one y variable. And inference means we're going to make generalizations about a population from our sample regression equation. All right? So now we're going to use our sample, there's a typo here, regression equation, that's what we're going to do, to make inferences, okay? And what we need are we need four assumptions to do that, okay? Before, we could just get a sample, we could get a regression equation, but we didn't need any assumptions because we didn't have to build any error bars around our slope. Now that's what we're going to do. And so we need to make some assumptions to do that. All right. So there's linearity and three assumptions about the errors around the regression line. And these three assumptions probably look familiar to you. Independence of the errors, equal variability, and normality, because they're the same three assumptions we needed to test group means using ANOVA. They're the same ones back on page 110. You can look, and you have these same three. All right? So, as usual, we're using those Greek letters for the population and the Roman letters for our sample, and then we're going to put these little hats on our predicted values. So here's in the whole population from which we took a sample, we have this regression equation where y equals some intercept and a slope times the x plus errors. And these three assumptions about the errors are that the errors are normally distributed with, zero average. You know, the errors have an average of 0, the errors around the regression line, and the same standard deviation across all the x's. That's the same sigma, and they're independent. So we should write that too. I don't have and are independent, okay? And independent. All right, now we have the sample regression equation. This is our predicted from our sample, and that's why we're using these Roman b's instead of the Greek betas. And we're saying that our prediction, that's a little hat for y, equals the intercept in our sample plus the slope in our sample, right? And we're not putting any errors around it because it's a prediction. If I left off the hat, I'd have to say plus error. Okay, and so y is an observed value of y, and y hat's a predicted value. All right, so now, suppose those exam averages and final scores of the 100, actually it was 107, but I rounded it to 100 here on our previous page. So n equals 100. From the previous example, this was on page 126. Okay? We're really a random sample from a much larger class of all stat 100 students during that semester, which was 2,000 about. Okay, so we took a sample randomly drew 100 students out of the 2,000, and then we get these sample statistics. So here are our sample statistics, right? These are them right here. So this is our sample average, that's x bar, and our sample SD, etc. And here's our sample correlation coefficient, and here's n. All right, so now how can we use that, the slope in our regression equation, to predict, to estimate the population slope? And how can we, how much sampling error are we going to have? So that's what we're going to do. So we have to set up a probability model. That's a box model, right? Like we always do. So let's do that. So we're going to imagine that there's a scatter plot here for the entire population. Okay, so this is going to be the entire population scatter plot with 2,000 points. So imagine there's 2,000 points in here. And we don't know what this looks like. So what's on the x-axis here? This is exams of all 2,000 students, and this is the final. So we'll have 2,000 points. I'm not going to draw them all in here, but we have 2,000 points. Okay? And one for each, just like we always do. This is our box model. Our box is a scatter plot. Okay, imagine that. So we have 2,000 points, one for each student in the population. Okay, there's 2,000 in our, that's where that comes from. That's the population. All right, so now what do? Imagine that we randomly draw out what we're going to randomly take up. We're randomly drawing out of all these 2,000 points, we're going to randomly draw out 100 of them. So we randomly draw n equals 100 students. Those are the points. Each, for each of you, you're going to have a final exam score and a midterm average, right? You're going to have those two numbers associated with you. So you'd be a point in here with two variables associated with you, okay? And so we randomly draw them from all 2,000 students, and they're without replacement. So that's our model. Okay, so that's the model. And then, now we have to check, so we get this scatter plot with 100 points. And now we have to check this scatter plot and see if the scatter plot satisfies our 4 assumptions. All right? Before we go on and do anything, we have to see if it satisfies these assumptions. And the first one is linearity. So we have to say, does our scatter plot with 100 points that we drew out of here, does it look like it will fit a straight line plus some scatter? Okay, so we have to check for linearity first. By looking at our what? Sample scatter plot. So, for example, if it looked like this, let's say it might look like, oh, I don't know, maybe it looked like something like this. Well, then we don't want to fit a line to it. That's bad. That's a curve. So this would be bad if it sort of followed a pattern like this, right? Or followed a pattern like, I don't know, it would be terrible if there was a negative correlation. Maybe there was a steep part here, like people who did really badly on the first were improving a lot, but then the middle students somehow did worse, and then these students did better. Something like that. I don't know if I'd see something like that, but that would also be bad. So this would be bad, and this would be bad. Why? Because it's not that we couldn't make a prediction, but we'd have to, we'd fit a curve. We wouldn't fit a line. We'd do something else. We'd transform our data or do something to fit, so that we're not going to try to fit a line when we have a curve there. So this would be bad. We're not going to go ahead and just fit a line to this because it doesn't fit. But something, so we want it to look like there's, to the extent that there's any pattern at all, it's linear. So something like that would be great. Okay? We don't want a curve. Okay? So if there shows a lot of curvature, we have to use some sort of other fit. So that's good. So then what do? So if that looks good, well then let's just get the equation. If we take our 100 points from here, it looks like this. Well, we say, hey, let's get the equation for this regression line. That'll be a nice approximation for whatever the true population regression line is inside there. So that's what we're going to do. So we did that last time with this same data, and we got, what y hat equals, how did we do it? We got 17, I remember this, 0.99 plus 0.67x, okay? And we did that by saying, we took these statistics, and we got this by saying r equals, how do we get this? Just to remind you, for this slope, beta 1, we said what? R times the standard deviation of y over the standard deviation of x. So in this case, it was 0.6 over the ratio of these two standard deviations. And since we were predicting finals, that was y from x. And so it's y over x, rise over run. So we have 10.3 over 9.2. And these are final points over exam points. So what this 0.67 is finals divided by exam points. So in this equation, you can see you have finals over exam times exam, and it reduces to just final points. And what this means is that for each, this positive slope means that for each additional point you have what you score in your midterms, your finals on the average go up by 2/3 of a point. That's our best prediction. That's what that slope means. All right? So that's what we've done so far. Now, so we look at this slope, and every time we take a sample, it's going to vary. So we want to measure, that's like the sampling error of the slope. We want to figure out the equation for the standard error of the slope. If we take another 100 points, it's not going to look like that. If we took another 100 points, we're going to get different points, so it's going to be a slightly different slope. So how do we describe the typical variation of the sample slope? That's called the standard error, the sampling error of the slope. And here is the equation for it. So let's think about it. So our sample slope, B1, right, that is a best estimate of our population, beta 1, but of course it's not exact. Since each time we take a random sample, we get a different set of points. So our sample slope will vary. That's the whole point. By give or take what amount? How much the sample slope typically varies is called the standard error, or the sampling error of the slope. And it follows its own square root law. Remember the square root laws? Like for the average, let me get a piece of paper just to remind you, they typically look like for the standard error of the sample mean, we have what? We have SD over the square root of n. Well, we're going to have where this is SD of the population, right? Now, and this is the scatter around the mean in the population over the square root of n. Now we have our own standard error of the slope that's going to be very, very similar. What's it look like? You'd think it would be, this part's hard to understand. You'd think it would be what? The standard error of the slope, this is just intuitive, the standard error of the slope, or of B1, right, is going to be the scatter, the standard deviation in the population around the regression line. That's called the standard error, standard deviation of the residuals, or the errors around our regression line. That's in the population. It should be sigma, but that's okay. Over the square root of n. That's what you'd think it would be, okay? But we also have that little standard deviation of x there, and I'll explain that in a minute. But let's just look at this part of it, okay? So the formula makes sense. The variability of the slope comes from the random errors of y around the predicted line. The bigger these are, the bigger the standard error is, right? So in your population, you've got some scatter plot. And let's say there was no error around it. Let's say our population looked like this, with 0 here. Then every time we took a sample out of it, we'd get the exact same thing, even if we had 3 points. So we'd have no sampling error. So the bigger, what we're saying here is the bigger that the standard deviation is, right here, the bigger the standard deviation of the errors, that means the bigger our sampling error is. You see, there's no error there, but if we add standard, let's say here's a regression line, our standard deviation of the errors is our scatter around this. Now, if there's a lot of scatter around it, well then, each time we take a sample, we could get this, I don't know, we could get something like this. We could get those 3 points. There's a lot of, the more scatter there is, the more our standard deviation goes up. And look at this part, the square root of n. If we only take 3 points out of here, we could vary a whole lot, right? If you take 3 points, like I just showed you, like randomly sample, we could get this point, and this point, we could get a negative correlation. Or we could get this point, and we could get anything. But if the bigger n is from here, the closer, the smaller the error is going to be. So the bigger n is, the smaller our standard error is going to be. That makes total sense. Now, where does this SDX come from? Let's look at this. So this standard deviation of the errors, do you remember the formula for it? It's the square root of what? 1 minus r squared times what? Do you remember? The standard deviation of y. So this, so this is in the population, and we're going to estimate it by the standard deviation, this from our sample statistics. So we're going to estimate from the sample SD errors. And our sample SD errors is square root of 1 minus r squared. This is like what we have, right? And then we thought we'd just have over the square root of n. But we have over the square root of n times SDX. Why? Well, the variability is described in terms of y. This is described in terms of y. And slope is change in y per unit of x. So we need to divide by SDX. We need, for 1 unit of we need finals over exams. We can't just have it described in terms of finals because it's a slope. It's rise over run. So we need it in the same units. So that's why that SDX is there. Okay? Does that make sense? Not if it makes sense. Does it? Just an intuitive feel for what it means. Okay, so that's where that part comes in. All right. So that's where this is. And this, you know, that's pretty obvious. And the SDX comes in just because of that. Just because we SDY over SDX. This is going to be an error bar around the slope. It has to be in the same units as the slope. All right, so now we need these assumptions of independence and equal variance to have come up with this. Why? Why did we need it to derive the standard? We didn't really derive it. I just said it why it made sense. But why do we need independence of the errors? Well, the idea is this, that we want to model our data as random draws from a large population, right? And so this n here depends on the draws being independent of each other. Like if there weren't, what does that mean if the errors aren't independent? If the errors aren't independent, that means knowing one error is going to tell you something about maybe another one. So basically you wouldn't have as, let's say like, so we really wouldn't have as large an n as what we thought. If the errors are correlated, so knowing one error gives you some information about the others, they're not independent anymore, and we'd have to have a smaller n here. So to use this formula with, n representing each error, then we have to assume that they're independent. So can we model the data as random draws from a larger population or as a random assignment to experimental conditions? So what do? We check the residual plot, and it should show no grouping. And this matters because if the points aren't independent, one example would be identical twins or triplets. Then in effect, we don't have as big a sample of n as we thought, because they're likely to have the same scores. You know, if there were, or clones or groups, or for some reason they're correlated errors. Okay, so you want to check that the scatter plot, and this is really important, shows no grouping. This is really especially important in time-dependent data because the errors might be related in time. So you have to check for correlated errors there. Okay, that's where it mostly comes up. So no grouping again. So you have x and y. So here's x and y, and no grouping, you know, that doesn't look like, you know, there's any groups here, right? But what would be bad? Bad would be you might have some points that don't show any grouping. You know, here you can fit a line, here you can fit a line. But maybe like you have some points like all clustered together here, and then like another group all clustered together here, and maybe another group. That's bad because it looks like these errors are correlated, okay? They're dependent. So that's bad, and this would be good. All right. People spend a lot of time when they're doing these models checking these assumptions. So I'm just trying to give you an overview here of why they come into play. If you have something like this, you have to adjust your n or do something else. You have to be aware that these errors aren't independent. Now, what about equal variability of the errors? The variability of the errors should be the same across all values of x. So you'd have to check a residual plot. And the spread should be about the same across the plot. Okay, so again, this is I'm just drawing a classic good-looking plot here. You know, and even if it has an elliptical shape, what do I mean? That the errors, the distribution in any vertical strip of the errors should be, the spread should be about the same. You might think this doesn't look good because it looks like the spread's more in the middle than at the ends, but that's just because there aren't as many points out here. That's all. You really assume equal variability across all the x's, so that's good. And sometimes you don't even know what's good until you see something bad. So I should probably show you something bad. I mean, it really is hard to know what's good unless you see a bad thing. So here's bad. So bad, a typical bad that happens a lot is something that looks like a fan. You still have this linearity, but you see how you don't have much error here, and then your error gets bigger as x gets bigger, and you have like a fan shaped. That happens a lot. And that's bad. There's not the same variability across. You have much better predictions when x is small, and the error gets big when x gets big. So that is bad. And it can be the other direction. They're fan-shaped. It doesn't have to be that way. You could, of course, have a fan, that went that way too. That would be bad. What we really want, is just the errors. If you look at the residual plot, it's a lot easier. Like if we were looking at the residuals, well, first let me just finish this. Okay, so why is this, this is bad because how much the scatter affects the slope depends on where along x it occurs, okay? So if you have something like this, and you changing, if you have something like this, you're going to have a lot of variability at this end, which is going to affect the slope a whole lot. You see, changing y near the mean doesn't tilt things much. But if you change y a lot at the ends, like if you have this or this, that's going to change. That's going to just affect your slope a lot. Okay, does that make sense? All right. We're using the same slope right here all along. So we want it to be, we're using the same error bar all along. This depends on equal variability. Okay, so now to check the assumptions, you can either look at the scatter plot like we did, but it's probably easier to look at the residual plot. So the residual plots we've seen before, that plots what? The errors. The errors are plotted along this is x, and these are the errors. And here, this is x and this is y. So this is easier to read. And here, what you usually have right here is the average is 0, right here. They're centered at 0, so it's easy to read. So this is the average of the residuals of the errors. And then you can see the spread. For example, you can see this distance. Just read it off easier. You can read it off easier there. You can just read it. It's like 17, whereas here it's harder to read. So and sometimes this scale is more spread out. Like I guess it is here, because this goes from 40 to 100, that's 60, and this goes from negative 30 to 20, that's 50. So it's a little magnified, so you can see it more easily. Sometimes you really can magnify it, and you might not be able to see the errors here, but you can see them there. Yeah?
Do the averages of the residual plots normally add to 0?
Do the average of the residual plots always equal to 0? Always, yes. That was a question, wasn't it, on one of your homeworks? Like the biggest residual, I gave you biggest residual, some number, the smallest. That was just to distract you. The average is always 0. That's just the way that, and that's why this spread around the average is like a standard deviation. All right. Now, okay, so now what are we going to do? Finally, let's just use this formula right here and attach a standard error to your estimate. Okay, so let's do that. So we said already that, I'll do it again. We said already that our estimate for the slope is what? Our estimate for B1 we said was R times SDY over SDX. And we did that. I just want to show you how. So we got 10.3 over 9.2, and that was 0.67. But that's a point estimate. Now we want to attach a range to it. So I want to show you how it makes sense to do this SDY over SDX, because here's our slope. Now what is our standard error of the slope? Let's write it right underneath. Our standard error of this slope is what? It's the standard deviation of our errors over the square root of n, and then it's times this SDX. That's the hard part to remember. But, so that's what? The square root of 1 minus r squared, I'm just writing it down again, trying to help you remember it, over the square root of n. And then you can think of it as, okay, this is the square root of 1 minus r squared times SDY, and now we have this SDX. So you can think of it as SDY over SDX, just like we have here. So here you have an r for the slope, and this is like a measure of the error around the slope. Okay, so now this is what? The square root of 1 minus, there's your r, 0.6 squared, right? That's 1 minus r squared times, I'll do this part first, over the square root of 100, that's our sample size. And now we have this same part. We can say 10.3 over 9.2. That's SDY over SDX. See how it matches up? This is going to be, so we're going to say, okay, we think our slope is, our point estimate is that, and this is going to be our give and take amount. And this part's the same, SDY over SDX. Okay? So, let's do it. So I did this. When I did this, what did I get? 0.09. Okay? So our range, we can call it our range. I just want to put some error bars. It's like a 68% confidence interval. That's going to be our sample slope plus the standard error. So that's going to be 0.67 plus or minus, 0.09. So it's like we're going to see it's like a 68% confidence interval. So we're attaching one standard error to our sample slope. And this is nice to look at here, because think about it. When the correlation is perfect. When you have a perfect correlation, you have 1 minus 1, you have 0. 0 standard error. That's like what we saw. 0. If all the points form a line, you have 0. And when that is, when the correlation's 0, when that's 0, then we have basically the standard deviation of y over x divided by the square root of 100. Okay. So that's the idea, and now let's just do confidence intervals. So we've already done this before, and we're going to just do the same thing now for the slope. We're going to use either the z or the t curve. All right, so any questions so far? Any questions at all? Nope. All right, so here's our old friend, the confidence intervals. All right. So, can we use a normal curve? That's the question. And t curves to use on the slope. So, we can. Why? We can use our usual confidence intervals based on the normal curve to say how confident we are that that a certain, like how confident are we that our sample slope plus or minus the standard error will capture the true population slope? How sure are we that if we actually calculated the true slope for all 2,000 points, we'd get a slope within 0.67 plus or minus 1 standard error? And I said we could be 68% confident. Why? Because we can, with a large enough sample, the probability histogram for the sample slope will follow the normal curve because of the central limit theorem. Since the errors in the slope come from the sum of n independent errors. There's our independence. And we know that the sum of n independent errors, if n is large enough, that's the distribution is going to follow the normal curve. So what do I mean by that? So I mean that if we sampled from the whole population, we'd know that right in the dead center here would be, as a slope, would be beta. Our true population would be right here, right? And then, but our sample slope, b, is going to vary around there. How much is it going to vary? Well, because this is the expected value, will be the true population slope, right? But we take many, many samples. We know that if thousands of random samples of n equals 100 from the population of 2,000 were taken and we computed the slope for each sample, we'd expect right in the middle, that's our expected value, to be the true population, beta. And as a z-score, we'd expect it to be 0, right? That's the expected value. And 68% of the time, we would get within what? Within 1 standard error. So this would be 68% of the time. Our samples, our b's, our Roman b's, the little b's, our sample slopes would be within 1 standard error. As a z-score, it would be between 1 and -1. And then 95% of the time, we'd get a sample slope between 2 and -2, okay? 2 standard errors from the true population slope. So we can be 68% confident that we land in here within 1 standard error of the true population, and 95% that we land in this region, etc. So that's the idea. And so in general, the interval, the sample slope, plus or minus the critical value corresponding to the confidence interval times the standard error is a certain percentage confidence interval for the population slope. Okay, so much easier to just show an example. Okay, so this z star, remember, is the critical value. Okay, so let's look at an example here. Okay, suppose we want to be 80% sure that the true population slope lies in our confidence interval. How many standard errors do we need to attach? So this question is the same as asking, this is exactly the same as that. Okay, so they're asking what z star is. what the critical value is for 80%. So you just, what is it? You just look at the normal curve, and here's 80%, and you're just looking for what value of z, and negative z is, gives you 80% of the curve. So let's do that. So what values of z should we do? So we just look on a normal curve. We've done this before. And 80% in the middle, this is our middle area, right? Middle area. And we want 80% in the middle. It looks like, well, it's a little bit less. We'll just use this. Here's 80% in the middle. It's 1.3. It's really like probably 1.28. We could use our P-value calculator. We'll look at it later. But for now, let's just say 1.3. Okay, we're round to 1.3. So between 1.3 and negative 1.3, so z star is 1.3. It's the positive one, you just say. Okay? So if we wanted to do an 80% confidence interval, what would we do? We'd say an 80% confidence interval is going to be equal to our sample slope, which is what would be 1, plus or minus this z star times our standard error for B1. So that would be, in this case, it's 0.67, right? That's what we have right here, 0.67. Plus or minus 1.3, that's our z star, 1.3. And then times our standard error, which we just figured out on the other page, 0.09. Oh, here it is. Right here. So that's the interval, okay? And if you added and subtracted, you could add, you take 0.67 and subtract that amount and add it. All right, so that's the idea. And so we could do the 90th percent. What would be the 90th percent confidence interval? That's going to be 0.67 plus or minus some z star times the standard error of 0.09. And you just look up 90% in the middle. So now it's going to be wider. It's going to go out further. We have to bring it out further, so our z star is going to be wider. It's going to be 1.65, I think. Let me just check. 90% in the middle. Yeah, 1.65. You see, as we get further and further out, our confidence intervals are going to, for more and more confident, we're going to have to make bigger intervals to be that confident. So this is 1.65. So we put 1.65 plus or minus. And then 95% confidence interval. It's going to be even wider. That's going to be 0.67. We know that. Plus or minus, we'll just estimate it as 2 times 0.09. And you see it's wider even, because now we want 95% in the middle. Okay, so they get wider and wider. All right, now the more confident you are. So this is the widest, and we're the most confident, 95%. We're most confident, if we went out really far, we'd be 100% confident, somewhere there. And this is the narrowest. Because we're the least confident, 80% confident versus 95% confident. The narrowest, because we're the least confident of these three. Okay, now let's see. So which of the following is true? This is the same thing. We have this, okay, so if we added and subtracted this amount, we'd get 0, this is 0.67 minus 2 times minus 0.18, that's where we get that, and so that's our confidence interval. So this is all the same. So the calculation was done right. This is correctly a 95% confidence interval. Now we just try to figure out who we should apply it to. So looking at these, do you see just, this is a typical exam question, so for sure circle what you think the answer is right now. Okay, so remember, the confidence interval can only be applied to the population the sample was drawn from. So where was it drawn from? It was drawn from all Stat 100 students, all 2,000 Stat 100 students for this one. So can we apply it to what? All female? Well, they're Stat 100 students. Let's say they were female Stat 100 students. For all female Stat 100 students. Pretend they were female Stat 100. No, because you can't apply. We're not sure that females are going to be the same way as males. You have to just, you can't, okay, so this is out because of the female. So that's wrong. And you certainly can't apply it to a different population. So this is wrong. And yes, for the exam scores of all 2,000 Stat 100 students. So you can't apply it. You can't apply it to a wider population, a different population, a wider population, or a more restricted one. Because we don't know that females are the same as males in terms of how their correlation between their exam and final scores, or a more restricted one. I mean, people make this mistake all the time, but think about it. If you take an election poll like Trump's popularity right now, what is it, like maybe 40% or something, or approval ratings, maybe low 30s, you certainly can't apply it to Democrats. It's going to be overwhelmingly more disapproving. You know, you can't apply it to a more restricted population. Oh, I see somebody asleep. Oh, you look so peaceful. I could show you to all the folks at home. Next time you fall asleep. Okay, I won't do it now. I wouldn't do it anyway, but just warning you. That would be cute. You look good asleep. Okay. All right. Now, here we go. So what are we doing next? Oh, our old friend, the t-distribution. He's not, well, by now, you know how to deal with the t, but there's a little, we're going to have different degrees of freedom than we did. It's not going to be n-1 anymore. It's going to be n-2. Everything else is going to be the same. All right. So now, this other assumption, the normality of the errors, where does that come in? That really comes in. We only really need that assumption if we're going to be using the t. Because if the sample size, because we don't really need it here, because we said assume n is big enough that the central limit theorem kicked in, that it kicked in. So we can use this normal curve and we can use the z. All right, but if we have a small sample, the central limit theorem might not have kicked in, and therefore we have to assume that the errors are normally distributed. Okay, if the sample size is too small for the central limit theorem to kick in, then if the errors are normally distributed, right here, we should use the t-distribution, just like we did for estimating means from small samples. So the same three conditions here, small, we'd have to have normally distributed errors around the regression line, or approximately normal, and an unknown standard deviation in the population, unknown standard deviation of errors in the population, which is almost always the case. So these S, N, U, then we can use T, SNUT. That's how you can remember it, that dirty word, SNUT. All right, so I just find it so tedious sometimes to deal with these little n minus whatevers and all different curves, but they come up so often, so we're going to go through them again. So now, all right, we've already done it with the mean. So just as our estimate of the standard error of the sample mean, like how much variability, each time we take a mean, it's going to be different, involved dividing by the square root of n minus 1, not the square root of n. Why? Because with 1 point, you can have no way of estimating the error around the mean. You have 1 point. You can estimate the mean, but you can't estimate the error around the mean because you only have 1 point. So you at least need another point to see how spread out it would be around the mean. So now our estimate of the standard error of the slope, we're not going to subtract off n minus 1. We're going to subtract off n minus 2. There's 2 degrees of freedom. Why? Because now Well, you know you can't compute a slope. You can't even get a line with 1 point, so you need 2 points to determine a line. But to get the error around that line, just like 1 point, you can do an estimate of the mean. You can do with 2 points, you could do an estimate of the slope. But to get the error around it, you know, you need at least a sample size of 3 to sensibly estimate the range of estimates of the slope. To get an idea, you need at least 3 points. Otherwise, you're just going to get the same slope you won't see any error around the slope. All right? So you need at least 3 points. So you can think of it as, so now we subtract off 2. All right? So if you have 1 or 2 points, you clearly can't do this. You need at least 3 for this formula to even make sense. All right. So now, so that's the only difference between our standard error for the slope is we do the square root of n minus 2, everything else is the same, instead of square root of n. All right? That's our only difference. So now, you could use this for the normal distribution. You can. It will give you a better estimate, slightly better, when the standard error is estimated from the data and not already known. We could do it. So we could do it for a large sample too, but when n is small enough for that to matter, the normal distribution is also starting to be inappropriate. And when we have a large enough n that we can use the central limit theorem, nobody bothers to do this. So, all right, so for small n, we'll use a t-distribution. So basically, there are 2 differences. All right, we'll use between the simple normal z that we showed and the t. So the first one is we're going to use this, we're going to divide by square root of n minus. Like in the last example, we would divide by what? Instead of the square root of 100, we would divide by the square root of 98. Okay, we use SE plus for t, and we didn't bother to do that for z. It's never wrong, we just don't bother. Okay, and we use the t curves instead of the normal curve, and as you know, it's probably good to see it over and over again. The t curves are fatter in the tail, lower in the middle, which means that for a given confidence interval, for a given confidence level, the intervals are wider. Let's go through it again. We've done this before. All right, so what do I say? The normal curve. Let me do it, highlight it. All right, so normal curve is this one that's tallest here, and then flattest goes really skinny in the tails, flat. See, it doesn't have much area in the tails. And it has more area in the middle, so it looks like that. All right? That's the normal curve. And then the t-curves are a series of curves. And if you have a tiny little sample, what's the smallest sample size we can have? The smallest sample we can have is n equals 3. Then our degrees of freedom are 1. So this k refers to the degrees of freedom. So let's look at that one. If you have n equals 3, then our degrees of freedom are equal to 3 minus 2, n minus 2, which is 1. So it's this one. Okay. So it's this. So this is if you have a tiny sample of only 3. And which one's that going to be? That's going to be the one that's furthest from. It's going to be this one that's furthest from normal. Going to have fatter tails. See, it doesn't go down, and skinnier in the middle. So now if we wanted to do a 95% confidence interval, we know what to do for the z. We're going to go for the z. What do we have? We're going to go like, this will be for the z. We'll go between -2 and 2, actually 1.96, but this is 2. This is equal to z star. Z star. And that means that this area is 95%. But how about for t? It's going to be a big difference when you have a tiny sample size. So this right here. So all this is 2. But now, what if you want to get 95% in the middle on this blue curve? You clearly don't have 95% if you went to 2. Look, could you have 95%? No, you have much less because you have all this extra here. That's 90. So that means we have to go out further. And see this little bit of extra? We have to go out further. So how much further do we have to go out? Well, to get 95% on this t-curve, a t with 1 degree of freedom, to get 95% in the middle, we're going to have to go out very far. Let me show you. Let's look in the book. And it's going to be much wider. So, all right, so here's our t-table. We'll have 1 degree of freedom. And so what do we want? 95% in the middle. This is if we want 95% in the middle, then it would be, do you see how we're going to use this? Because this only gives us, this is for 2.5% on one tail. So we'd have 2.5 and 2.5, and this would be 95% in the middle, right? We want 95% in the middle. So we need 2.5 in each tail, and that's what this table does, just the right tail. So here we are, and look at our critical value. It's 12.71. That's because the sample size is, we're going to have so much error if you only take 3 points, right? So let's draw that. And this is what our critical value would be. What I want to show is that T star is greater than Z star for any given confidence interval. And when you're using this tiny t curve, we'd have to go out to, shoot, what did I say, 12.71? So it'd be, let's pretend this here, 12.71, that's T star. Then we have to go out the same, pretend it was way out here, 12.71, that would be negative. That would be T star. And then we'd have, oh my gosh, it would be, so this would be our confidence interval, huge. It would be symmetrical. I have to go out as far in the other direction. And that would be 95%. Would be between those because it's so much lower here. So we have to go out further and catch this. And this area is tiny, So that's what it would look like. Let me show you on a Pvalue calculator. It's so much more fun. All right. So let's go on the Pvalue calculator. You should do this yourself. All right, so we'll go here. Whoops, we'll go here. All right, so for the normal distribution, if we want, okay, let's do the t distribution. Let's go to t. So what do we want? If we have 1 degree of freedom here, and we want a middle area equal to 95%, so I'll put in 95% there, and now we want to see what the critical value of t is corresponding. There's the 12.7, and see how far you have to get. Huge. But now let's say that's a sample size of 3. Let's say our cutoff's 25 is what we're using. So 25 would be how many degrees of freedom? N minus 2, so it would be 23. So let's check it out for that. So it would be 23. And let's do for 23. And now we want to compute a t. See, it's about 2. It looks much more like the normal curve. All right? So that's why I say at this point we might as well use the normal curve. Okay? Does that make sense? That's the idea. All right. So we've got that. And now we're going to do an example using t. So let's do it. Go back to the document camera. And here's an example. So people, let's look at this correlation. Let's say you wanted to see if, how GPA is affected by drinks. Most of us think that by drinking. Most of us think that it stands to reason, you drink a lot, you're going to lower your GPA. So suppose we asked a randomly selected group of 25 U of I students. I asked you guys, and we got a slightly negative correlation. Let's see if we asked 25 U of I students how much they drank per week and what their GPA was, and got these 5 sample statistics. We can't sample all 28,000 undergrads, so we want to get an idea about it. So we're just taking a random sample of n equals, this is our n. These are our sample stats. What do we want to do? And we want to predict GPA from drinking. So this is going to be y, whatever we're trying to predict, and this will be x, because y? Because y, like right here, is whatever you're predicting. This is confusing. You don't need a star there. But y is whatever you're predicting. Okay? So this is the idea. And so what do? We set up this probability model. All right, so the probability model always, that's a box model, it's always about the whole population. Remember, it's always the whole population. Probability model is always about the whole population that you're sampling from. Okay, so we have a scatter plot that's the whole population. So it's going to have approximately 28,000 points, one for each UIUC undergrad. If that's who we're randomly selected group of U of I students from all UIUC students. All right, so that's the idea. So you got these 28,000, we don't know. Inside here, we really don't know. There's just a ton. So now what do? So what is here? So this is drinks, and this is GPA, and we want to see if it's negative inside here. So we randomly draw, that says draw, randomly draw, n equals how many? Where is it? 25. N equals 25 from here, and it's without replacement. And then we get these sample stats. So these are our sample stats, okay, right there. That's X bar and so forth. These are to get our sample stats. So we get this. And we get, that's really important. It's negative there. Okay, so we see this negative correlation, and we say, okay, we get all these sample stats, and we say, okay, can we conclude there's a negative, that's what we thought. It looks kind of small, though. Can we conclude there's a negative correlation here? We think there is, but now we're not sure because we only have a sample size of 25, and it's going to change each time. So calculate that. So first, from here, so we have this equation. Our predicted GPA is going to be equal to some intercept plus a slope times x. And to get our slope, we're just going to say r times SDY over SDX, and that's negative 0.2. That's our r. And then we have to, okay, so here it's going to be y over x. 0.5 drinks, no, GPA points per GPA. No, per drink. Ellen, let me write this out. What is that? So that's negative 0.02 points, GPA points per drink. So what does that mean? That for each drink on the average that students drink, on the average their GPA gets lowered by that amount, by a tiny little bit. That's what that means. All right? That's in our sample. But maybe we don't know if that's true in here. That's a tiny little slope. Maybe in our sample small. So we have to say how much does it vary? What's our standard error? So here we're doing the standard error, because we have only 25, we're going to do the standard error of this. Okay, so we're going to say it's the square root of 1 minus r squared over the square root of what? N minus 2 times SDY over SDX. So we'll do that. The square root of 1 minus negative 0.2, that's r squared, over the square root of what? 25 minus 2 So that's 23 times that, 0.5 over 5. Again, it's points per drink. And I got at 0.0204 points per drink. All right, so that's what we have. And now we want to use the t to build a 95% confidence interval for beta. So we have to ask ourselves, all right, so the confidence interval has this form. What? This. We know this part. The sample slope is negative 0.02 plus or minus something, that's t star, times our standard error. And our standard error we know too, 0.0204. And it's in the same units, right? Okay, so that's it. We just have to get that t star to put in here. So we want to put t star in there. So how are we going to get t star? Okay, so which curve are we going to look at? The degrees of freedom is n minus 2, that's 23, because degrees of freedom are equal to n minus 2, which is 25 minus 2, which is 23. It's the same as this. All right, so we've got that. So now we have to, we just looked, I think we just did it for a sample of 25. Yeah?
Is that always going to be your degrees of freedom?
The degrees, okay. It will always, the degrees of freedom are always n minus 2. Okay, because degrees of freedom for simple regression, one slope, good question, are always equal to n minus 2. And here we have, so 25 minus 2 here. Okay? But not, this isn't going to be, we're going to add another variable, like this is a line, we'll add another variable, it'll be a plane, and then it's going to be n minus 3. So it's basically, I'll explain it right at the end of the hour, how it is in general. But let's stick to our example now. So we just saw it on this, I remember it was 2.07, wasn't it? We just saw it when we looked at the calculator, but if you didn't, let's say you didn't have that, so we could look here, and now what are we doing? You didn't have the calculator, and now you're saying, okay, 95% confidence interval, and degrees of freedom are 23, and there it is, 2.07. All right, so that's what we're going to use, and that's what's going to go right in here, 2.07. All right, and I did that, added and subtracted that, and I'm doing it out because I want to show you that it includes 0. So I got negative 0.062, and the upper limit is not negative. So we're 95, because we're wondering whether it has a negative slope in the whole population, but it extends all the way into the positives, into 0.022. So our confidence interval includes 0. That means we can't be 95% confident that there's a negative correlation in the population. In other words, a small negative slope in our sample could easily be due to sampling error. And we're going to see that this 95% confidence interval, including 0, is equivalent to what? Not rejecting the null. Not rejecting the null for the two-sided at 5%, 2.5 in each one. We'll look at that more next time when we do a hypothesis test. We're going to look at this a lot. But for now, this is what we got. Now, what if we wanted to use? We're right on the borderline there. What would change if we wanted to use Z? So now we're going to try to use Z. Right away, will it be wider or not? Remember, the T is always wider. Look, will it be wider than using T? No. Remember this picture. It's going to 95% is going to be narrower, and it's because we have it higher here. It's wider using T. Yeah.
Oh, question on B. What did you get? Should it be negative 0.0?
Here?
Negative or B? Should it be negative
This?
0.03 or 0.02? B.
B, 9B.
B.
9B be here. Where did I get this?
2, wouldn't it be negative 0.02, or is that a 2?
This is 0.5 over 5, right? So that's 0.1, so we just move it over 1. See?
Oh, that's a 2 there?
This is a 5 over.
Your answer, is that a 2 or a 3?
This is a 2.
Oh,
Oh, you thought it was 3? Yeah, yeah, sorry. That's a 2. Sorry, my handwriting's bad. Okay.
That and you use that in the bottom. That's where the negative 0.02 came from? Right.
I'm using this negative. Sorry, the numbers are all the same. Like, this is so confusing. It looks like, oh, this is about the same. No, this is just a total coincidence because I made this easy. I kind of I made this easy for me to do in my head.
Gotcha, okay.
That's the only reason. They're usually not the same.
Okay.
Good point. Okay, now back to here. So now they're going to be wider using the T. Okay. Now, wider, yeah, will be wider than using the T. Z is narrower, remember. Okay, now what are we going to do here? First we have to change this standard error for the slope. What should we do? We already did this. Now, we already did this one. Now, how are we going to change it here? This is too confusing. Let's just do standard error for the slope without the plus is what? So it's going to be, I'll show you what it will be. So you'll have 1 minus r squared. It's going to be, everything's the same as this. Let's just copy it. Everything's exactly the same, except for what? This part's the same. This part's the same. What's the only thing that's different? Instead of putting the 23, the square root of 23, I'm going to put what? I don't have a plus here. What am I going to put? Just n, right?
Yeah.
So 25. So these are identical. The only thing we're looking at is this versus that, right? So this is smaller. That's why we have a plus here. It's bigger because we have this, okay? So if we were looking here, if we wanted to see which one we want to circle, well, we're taking this one and we want to change it, so it's going to be, we want to make it smaller from a bigger. So we're going to divide by, this is less than 1. This is like the square root of 23 over 25. So if I multiply this by the square root of 23 over 25, I get rid of those 23s, and I get that. Does that make sense? Does that make sense? All right, I want to get the standard error of the slope. I want a square root of n in the denominator. So I want this to have the square root of n in the denominator. Just think of it that way. You're just going to have an n, square root of n in the, if I want to get this standard error of the slope, I want a square root of n in the denominator. So I don't want to do that. All right, so that's the idea. And if we do this, what do we get? If we do this, I get, well, this one's easier. I could either just do this calculation, but I think it's easier to do this, and I get 0.02 for this one. Okay? Because that's just a 5. And now, plus I did the calculation already. All right? So that's what we have here. So our 95% confidence interval is exactly what we did before. Negative 0.02. Now it's plus or minus. Whoa, I needed Z star in here. Z star times our standard error, not the standard error for the plus. All right, so this is our standard error, but what's our Z star? Should we just use 2 or 1.96? Let's just use 2. So we'll get negative 0.02 plus or minus 2, that's corresponding to the 95%, times 0.02. Okay. And this is easier. So we have negative 0.02 minus 0.04. So that'll take us all the way down to negative 0.06. This takes us a little further down. And this will take us up to 0.02, positive again. It's a little bit narrower. See? That was a little bit wider. Because we have 23 degrees of freedom, not 1 degree of freedom. So that is the idea. And boy, it's a lot of concepts and a lot of explaining, but I want to get back to her point about how are we going to figure out these degrees of freedom and what's a systematic way to do it, the question before. So why don't we say, okay, so we use a t-distribution. Here's the degrees of freedom. So in general, this is an easy way to figure it out. The degrees of freedom are equal to your sample size n minus what is the number of parameters we're estimating in the model. And this is going to come up over and over again. Minus the number of parameters in our model. So we can call it n minus p. P is the number of parameters, not a probability, not a p-value. Okay? This is the number of parameters. So the degrees of freedom refer, as I can think about it, to the variance, the scatter, the variability around your model. Okay, so starting with, so the variance around the mean has n minus 1 degrees of freedom because we only have one parameter. We're only estimating, because our number of parameters equals 1. We have one mean. We're estimating a population mean. The variance around a line has n minus 2 degrees of freedom because we have two parameters. We're estimating beta naught, the intercept, and beta 1, the slope. What we're going to see pretty soon when we add another variable is the variance around the plane, if we have a plane, has n minus 3 degrees of freedom because the parameters are equal to 3. We're going to 3 points determine a plane, right? So we're going to have a beta naught, we're going to have a beta 1, and we're going to have a beta 2. We're going to add another variable, etc. And this can be applied to ANOVA too, to our groups. We had 3 group means we were estimating, so one of our sets of degrees of freedom was n minus g, n minus the number of groups. So this is a basic way you think of it. How many estimates, how many parameter estimates you're making in your model, and it's n minus that amount. Thank you for asking. Okay, take care.